Hello friends, this is Coach Veer on my YouTube channel Coach Veer, and today we will discuss about half factorial, which is equal to square root of pi upon 2. That's a very peculiar result, and even few of my friends, they might not be knowing this result, that factorial for non-integers like half or 3 by 2 like that also exist, and there is a way to prove this. So that is the generalization of factorial function. Factorial is just a function, and we will discuss about this in this video with a proof also. That's going to be very long video, so be with me. And before starting this, a request to you, as I always do, please subscribe my channel and share it to all your friends, and like is appreciated. Thank you. Let's start. So let's go with the few basics like factorial. If you have heard that 0 factorial, by custom we take it as 1, or you can say by convention 1 factorial is 1, and 2 factorial is the multiplication of 1 with 2 or 2 with 1. You can write it as this way. This point is multiplication. Okay, so 3 factorial is 3, 2, 1, and so on. Like n factorial, if you say, that means n multiplied with n minus 1, then reduced by 1 more, and so on till 3, 2, 1. Lastly, it will end with 1. So that's how the factorial function, where n belongs to the z plus, or you can say natural numbers or integers, positive integers, we will do it like this. But what about the half? That is not defined in smaller classes, so we will deal with this. But before dealing with this, I have you must know about generalization of the factorial function, that is the gamma function. So we will talk about now gamma function. What is gamma function? How it looks like? It looks like this type of function, this type of shed type, and these lines are straight actually, and like it is defined for x like this. Okay, this gamma function. Now what is this function means? It means that there is a few theory why we are taking this gamma function, because it is the only function which satisfy the properties which are required to solve this, that is convex and for the logarithmic function and other stuff. Let's show you what is gamma function. This is our gamma function. Now in this gamma function, you might be seeing that if it is defined for z, it means 0 to infinity e to the power minus t z minus 1 dt. Okay, you can write it in this way also, 0 to infinity, as it is multiplication is commutative, so you can write t to the power z minus 1 e to the power minus t dt. The same thing only. So now here you see, this is the graph of this function. So graph of this function, you can see if 1 is there, you can see the value is 1. Okay, so the value is 1 comma 1 at 1. Now at 2 it is going to be reaching 2, so it looks like this. So now the point is that at this we have a dotted line like -1, -2. So gamma function is not defined for negative integer. That is what by this graph I want to explain you. And for a negative rational number, it is defined and the values are written here. So the important value which we want is gamma of 3 by 2 is equal to root over pi by 2. That is how we need to prove this. And how we will prove this, that I will explain you. Suppose we have a gamma function and gamma x plus 1. You need to know that gamma x plus 1 and factorial function are related. Like x factorial or you can say n factorial. Let me write it in the terms of n plus 1 factorial is not needed in this, is equal to n factorial. That is what I am going to tell you. Now if you have, suppose, and there is a property with the gamma function, like if we have a gamma n plus 1, then it is equal to n gamma n, like it is reduced by 1 and that the number will come outside. This is the property of the gamma function, you can see, and we can prove this with the help of this integral which is given there. But the important part here is, if we have let me make it more clear. Okay, let's start with gamma of 3 by 2. So what we got by the definition, that 0 to infinity y to the power 3 by 2 minus 1 e to the power y dy. Hope this is clear to you. How? By using the definition. You can see 0 to infinity x to the power z plus 1. So it is going to be like this. So if we solve this further, what we are going to get here is 0 to infinity y to the power 1 by 2 e to the power y dy. This is what we are going to get. Okay, now this integration we can solve by parts. So this is the first function, this is the second function. So applying by parts, what we are going to get here is, first function is written same, so I am writing y to the power 1 by 2. Then the differentiation of the second function, it is e to the power minus x, so it is minus y. So here we are getting the integration of this is minus e to the power minus y. Okay, and the limits are from 0 to infinity. Now put a negative sign and do the differentiation of the 0 to infinity is the limit. Now differentiation of this is 1 by 2 y to the power minus 1 by 2, correct? And integration of this again is minus e to the power minus y dy. Hope this you know this, that first function, then integral of the second function, put a subtraction symbol, integral d by dx of the first function multiplied by the integral of the second function, and then the whole are integrated. So now substitute the value here in the first part. Let's solve this part. So you know, when we put y is equal to infinity in this, what we are going to get? So infinity to the power 1 by 2 minus e to the power minus infinity. E to the power minus infinity is 0. Okay, and let's substitute 0 also. 0 1 by 2 negative e to the power negative 0 is this part. So you can know from there that this part is going to be 0. So 0 into something is 0, 0 minus 0 is 0. So this part is totally 0. No need to think about this part. Now we will talk about this part only. So what we are left with here is 0 to infinity half I can okay, half. Let's do one thing. I will write it in this form, like y to the power 1 by 2 y to the power 1 by 2 in negative, and this negative become positive going outside, e to the power negative y dy upon 2, correct? So here we have to make a substitution. Let's check what we substitute. If we substitute, let's say u is equal to y to the power 1 by 2. So what we are going to get? We are going to get here is du is equal to 1 by 2 y to the power negative 1 by 2 dy. This is working here. So let's apply this substitution. After applying this substitution, we can say Okay, let's do a little bit work here so that later you will know. Squaring both the side, you will get u square is equal to y. Okay, so y, in place of y I can put u square. So what I get here is 0 to infinity. This whole part you can see here in this, and we can remove this. I will make a bundle like this part can be removed and put it just u. So, and this part we can put e to the power minus u square du. Hope this is clear to you. We got an integral in this form. Now the task begins. This whole integral is actually solved with a little bit changing the you can say this is our I coordinates. Here we have a clever trick. You can say if I have to do like, if this is a definite integral, correct? It is a definite integral. So definite integral is a value, and that is not going to change if we change the variables. So if I change the variables like 0 to infinity, or let me do a little bit work. If I take in minus infinity to infinity, why I am doing this? Because there is a Gaussian integral involved here, and Gaussian integral I am doing it the hard way. Okay, so you might not be understanding this integration, but I will try my best to make it as easy as possible for you guys. Okay, so if I do it like this, leave this person here, leave this as equation which is important equation. Okay, so I am leaving this as here because we need a result which is equal to this, that is only equal to our thing, which is gamma 3 by 2. Okay, let's start from here. Check out this first. So suppose we have e to minus infinity to this minus u square du, and another by variable change I have minus infinity to infinity e to the power minus s square ds. Then if we multiply both of them, then it is going to be a double integral. I square is equal to negative infinity to negative infinity. I can write it in this way. So what I am going to get, e to the power negative u square and negative s square, both are in multiply. I can take negative common and write it in this way, correct? ds or du, anything you can write. So this is how we can summarize this. Now here comes the dimensional analysis, the area which we need to find by the antiderivative, but it's not easy, you cannot solve this. Okay, it is like finding the area or the volume below this curve, in this curve. So let's use another theorem, which is Fubini theorem, which will help us in solving this. What it do, it changes it into R2. But better we can write, instead of two integral, we can write in a single integral also. It's because R2 is mentioned, we are talking about some area thing where the two coordinates are involved, and the definition said that if we have this thing, then it is equal to this single r times single r f of x comma y dx dy. This is what this theorem says. Okay, let's utilize this theorem in our work. How we will do that? We will just represent this fz by this. So what we got, and you can use the substitution. Instead of that z, you can put here as z. So let z mod of x comma y, you can say like this, is equal to root over x square plus y square. So you can put e to the power minus x square plus y square is equal to e to the power negative of x comma y whole square is equal to e to the power negative z whole square. Correct. What I have done? I have done substitution. In place of this, I have put it z square, but in mod, as it is the distance. Okay, so let's substitute this value, and what I have got here is I square is equal to this double integral type r square situation, e to the power negative of mod z square dz. Hope this is clear to you. Now I am changing the coordinates. We calculate some integral in different coordinates. Okay, we use here polar coordinates. So in polar coordinates, what we do here is we think of z in r cos phi, r sin phi, and this phi belongs to 0 to 2 pi and r belongs to 0 to infinity. Okay, so we calculate this under this situation, and what we got here, we change the limit. So first limit is 0 to infinity for this part, r part, and another limit is 0 to 2 pi. You can see the another limit for this is 0 to 2 pi. So we can say e to the power minus r square r d phi into dr. Okay, done. What I have done, I have put it the magnitude. Okay, x square and y square, you know how we do, and r d. This is quite easy. Now here the situation comes, and we can solve it very easily if we separate the r thing. Now we know the r is to be integrated with this integral, so I will take r thing outside of the first integral, and in the first integral I have, instead of anything, I have d phi only and 1, you can say, and this whole part we can integrate. Okay, and after this we have the dr part. So you know integral of 1 is x only, so integral of this is x only, and this integral x is having the limit 0 to 2 pi. So let's substitute this limit, and what you are going to get, 2 pi, simply 2 pi. So I can take this 2 pi outside, and what I am going to get is 0 to infinity r e to the power I my negative r square dr. Now it looks very simple to us, as substitution will work. So let r square is equal to t, you can say as t, so 2r dr is equal to dt. So let's substitute the values. So what we are going to get is 2 pi integral 0 to infinity, and limits also you can change, but it's infinity square is infinity, 0 square is 0, not required. So what we are going to get here is e to the power negative t dt. Now you know the integral of e to the power negative t is negative of e to the power negative t, and then you put it the limits 0 to infinity. When we put the limits, you know negative can be coming outside, or you can put the first 0. So negative e to the power negative infinity, negative positive, e to the power 0, negative 0 or 0, both the things are same. So when we do this calculation, e to the power negative infinity, you know the e graph is like this. So when you are going towards the negative infinity, it is going to the 0 values. So I will put here 0, and e to the power 0, if you seeing e to the power 0 is here, it is equal to 1, so I will write 1. So you can say it is equal to 2 pi. So what I got here is I square is equal to 2 pi. So I square is equal to 2 pi, then I is equal to root over 2 pi. Hope this is clear to you, or any doubt in this? Maybe you might be having doubts. Yes, the doubt I have also is here. When I substituted it, I removed this 2r dr. Then what this 2 is doing here? This is being divided by this 2, or you can say I have to take this in the division. Yes, that's what I had done a mistake here. Okay, so I is equal to root over pi. Okay, so our integral what we have got here is I is equal to root over pi. Let's move to the important part. Yes, so this whole part, but we have seen that we have done it for negative infinity to infinity, e to the power minus u square du we got as root over pi. So if this area, you can see from the negative infinity to the infinity we have the double area. If we want the half of that part, we need to divide it by 2. So 0 to infinity, e to the power negative u square du will be half of that. Hope this is clear to you. This is quite long thing, but I'm able to do this. Few mistakes also, sorry for that, but it's kind of long. Okay, so here we got as this. Oh, it's quite long, really. So that's how we change. And if we find it one of the value by the property, that property which we have just learned, that if we subtract the inner part by 1, we can get the number outside the gamma function in multiplication. Like if we have 5, so we can have it 4 gamma 4. Oh, 5 gamma 4. We have reduced the inner part by 1, and we have taken this outside. Okay, no, it's 4 only. So that's this. So this is quite complicated for me also, but not that much. It depends how much you use this type of functions in your work, and it's quite interesting function from the application point of view in the fractional calculus, or most importantly in the fractional calculus, because all the definitions use this generalized gamma function or generalized Euler functions. That's very important kind of function in this fractional calculus. What I mean by fractional calculus is, like you calculate d by dx, but what if the power is half, or the order is half, not the power, order is half? Then what you going to do in this type of situation? We utilize the definitions of Caputo and Riemann, and they utilize the gamma function in their definition. And if we know the gamma function, we are able to solve those half derivative or the 3 by 2 derivatives. Otherwise it's quite not possible, I think so. So here we have proved that half factorial is root over pi by 2. These type of interesting things I'm going to put on my this channel, and if you subscribe and press the bell icon, you will receive these type of interesting mathematical functions or notations, like that type of stuff usually. So please subscribe my channel and share it to all your friends who love mathematics like I do. Thank you for watching this. See you in my next video. Till then, bye bye.